Good day and welcome to our CARDS 2021. It will be my pleasure to talk to you today about some of the work done in the food technology team over the last year towards building an evidence-based toolkit for monitoring cocoa fermentations to optimize bean and flavor quality. We'll be doing a tag team presentation today with different team members presenting different sections. So let's get right into it. By way of outline, I want to firstly set the stage by introducing the topic and looking at the importance of fermentation, whilst considering the gaps, rationale, and aims and objectives of this study. We will then look at some of the materials and methods. I will then tag in the rest of the team to bring in different parts of the results. And then we will focus on linking all of the results together to the fermentation dynamics and flavor attributes with some key take-home points and the impact of the work. So let's get started. Sometimes there's confusion when the word cacao should be used and when the word cocoa is more appropriate. No general rule is applied consistently. Some use the term cacao when describing the scientific and horticultural aspects of the plant, switching to cocoa once the bean has been fermented and dried, or with products made from the beans. Both terms are correct at any time and virtually interchangeable. Cocoa is the term that I'll be using throughout this presentation. This presentation speaks about cocoa fermentation, and I just wanted to define what is cocoa fermentation. It is basically a spontaneous microbial succession of a wide range of yeasts, lactic acid, and acetic acid bacteria. And during fermentation, the mass of beans increases in temperature to about 50 to 52 degrees centigrade, and the microbial products such as ethanol, lactic acid, and acetic acid permeate through the seed coat into the seed tissue. The elevated temperature and microbial products cause seed death and the production of flavor precursors by breaking down polyphenols, storage proteins, and carbohydrates. Fermentation and drying is responsible for unlocking the genetic flavor potential of the different varieties. Without fermentation, cocoa beans are bitter, astringent, they have no aromatic flavor development, and they have a thick and pasty mouthfeel. You can see the difference in the cotyledon color in the slide here, where the unfermented bean is very purple and slaty in color and contrasted to the well-fermented bean that has a rich chocolate brown color. Looking now at the gaps, rationale, aim, and objectives of this work, we have many variables affecting fermentation in cocoa. We have the mixture of microbes, the wet bean substrate, such as the bean pulp, sugar content, and moisture content of the pulp. We have the ambient environment, the temperature and moisture in the atmosphere, the type and size of the fermentation vessel. All these affect the rate of fermentation, and studies linking these variable factors to fermentation progression, turning regimes, and fermentation endpoints are lacking. So this is the gap that we are really trying to explore with this work. The rationale for this work arising from the gaps is that a rigid recipe book approach is usually applied to fermentation, with fixed practices and fermentation times, etc., that actually occur in a very dynamic environment. Certain things need to be flexible, and this hit and miss approach to quality often results in poor or inconsistent expression of genetic flavor potential. The specific aim of the study is to find the best indicator or indicators for determining the optimal fermentation endpoint. The objective is to investigate the impact of the quality of wet beans, local environmental conditions, on the fermentation progression, fermentation endpoint, and the final quality of fermentation as expressed by the flavor profiles of the beans. Looking now at the materials and methods we employed, bean fermentation data were collected over multiple harvests, with fermentation batches occurring between December 2019 in a pre-COVID environment all the way to July 2020, during our first COVID lockdown from March to early July. We broke up these harvests to coincide with an early, middle, and late season, recognizing that some of our middle and late season harvests were missed due to the lockdown. Data collection was done at 2 different farms located in different agroecological zones in Trinidad, one in the central north region of Santa Cruz and the other in the western flank region of Grand Couva. Both locations had box fermentation systems that were either in a cascade or inline arrangement, and the fermentation mass was turned twice. Beans were dried via open floor sun drying with a sliding roof system over the drying floor. The following variables were measured over the multiple harvests. We had the environmental attributes, looking at ambient temperature in the night and day, as well as relative humidity and the barometric pressure. We had the wet bean attributes, looking at the pulp, the percentage moisture content, the pulp index, the total soluble solids or sugars, and the initial pulp acidity. We also looked at the fermentation dynamics, the external and internal bean changes during fermentation, the time to reach 45 degrees centigrade, the time for the intersection of the cotyledon and tester acidity, the time taken to reach the maximum fermentation temperature and what that value was, as well as the sensory attributes of the liquors that were made from bean samples, focusing on core attributes of cocoa flavor, acidity, bitterness and astringency, complementary flavors of fresh fruit, brown fruit, floral, woody, spice, nutty, and sweet notes, as well as any off flavors that were present. Samples were collected from fermentation days 0, 3, 4, 5, and 6 for the various assessments. Cocoa liquors were prepared from and sensory evaluation carried out on samples from the drying floor, as well as those collected on fermentation days 4, 5, and 6. Sensory assessment was done in a completely randomized block design with 3 technical repetitions by trained panelists across 38 flavor attributes using standard methods. Okay, I will now hand you over to Lincoln McDonald to start the conversation on the results from the first set of assessments and bean collection.
Hi, good day, everyone. My name is Lincoln McDonald. It's a pleasure to be speaking to you today. Today, I'll be doing a presentation on the trends on the data collected, on the environmental conditions, along with the weights, the wet weights of the beans and their attributes. Firstly, I'd like to dive into the environmental conditions. The environmental conditions were recorded or collected by mounting 2 data loggers. One data logger was mounted into the Grand Couva area and the other into the Santa Cruz area. As you can see, with the data in front of us, we saw that the daily average ambient temperature along with the barometric pressure were fairly similar in both locations, unlike the average nightly ambient temperature where we saw there was a 3.2 degrees Celsius increase in the Santa Cruz area versus the Grand Couva area. Now on to the average ambient relative humidity, we saw there was a 3.4 increase in terms of percentage in the Grand Couva versus or compared to that of the Santa Cruz area. Now, I'd like to move on onto the wet weights of the beans received across the growing season for both locations. Firstly, I would like to focus on the wet weight of the beans received at the Santa Cruz area versus the Grand Couva area. As we can see that in the Santa Cruz area, there is initially a higher amount of beans received, and this is due to the larger capacity of the fermentation boxes in the Santa Cruz area versus the Grand Couva area. Across the season in the Santa Cruz area, all 3 seasons, we saw there was an average of 1,021 kgs of beans received across the season versus that there of the Grand Couva area, where we saw there was an average of 456 kilograms of beans received in the Grand Couva area. A common trend we saw in both locations was that there, in the mid-season to the late season, there was very similar in terms of the decrease but with the smallest decrease occurring in the Santa Cruz area. Now moving on to the average wet and dry pulp percentage of the total bean in both locations. This was done by using a 25 bean sample, where we use the pulp content of the 25 beans. This 25 bean sample was determined by doing small trials or some trials where we looked at the minimum amount of beans required to get the smallest value in terms of standard error. Okay, so if we could look at the wet percentage in terms of the total bean in both locations, we saw that there's very similar in terms of the values, where the peak or a peak occurred in the Vancouver area in terms of the mid-season, and a peak occurred in the late season for the Santa Cruz area. Now on to the dry rate. In the Vancouver area, we saw fairly consistent across the 3 seasons, and in the Santa Cruz area, we saw that there was a very slight or gradual increase in the percentage across the season, from the early season to the late season. Now moving on to the average wet and dry pulp index for both locations, building on the calculations before where we did the percentage in terms of the total bean. As said before, we did something called the pulp index. The pulp index basically is the amount of pods required to get 1 kilogram of pulp, and providing that each pod used was or contains a 40 beans per pod. Right. So if we could look at the wet pulp index for both locations, we saw that it's fairly consistent, or somewhat very consistent in the values. Moving on to the dry pulp index now, we saw that the values compared to the Santa Cruz area, the Vancouver is fairly or slightly higher than the Santa Cruz area. And in the Santa Cruz area, we see there's a general or very slight decrease in the value across the season. Moving on to the average total soluble solids. As we know, generally, the sugars are the most abundant total soluble solid in fresh fruit juices, and this could be expressed in terms of the percentage of bricks. Okay, if you can look at the Vancouver area, you see there's a steady increase in terms of from the early season to the late season in terms of the percentage of bricks, and this could be due to or represented by the pulp having, or the fresh pulp having fairly sweeter pulp compared to the early to the late season. Right? And this is in the Vancouver area. Unlike the Vancouver area, we see in the Santa Cruz area, where the initial total soluble solids tend to decrease from the early to mid-season, but the mid-season to the late season, we saw that there's an increase, and this could lead to implications in terms of the fermentation rate and the microbial activity in the fermentation or the fermentation cycles. Moving on to the average initial pulp acidity in terms of pH, we can see in both locations. First, we go on to the Vancouver area, where we see initially there's a higher pH compared to the Santa Cruz area, and in the Vancouver area, we saw that there was a slight or gradual decrease in terms of the pH, meaning the pH tends to be slightly more acidic. And in the Santa Cruz area, we saw that the pH from the early season to the mid-season decreased and increased from the mid-season to the late season in this location. Now, I'd like to give you over to my colleague Krystal Daniel, who will be presenting on the fermentation dynamics. Thank you.
Hello, everyone. Good day to you. I'm Krystal, and I will be picking up from where Lincoln left off. I want to look at the external and internal changes to the beans during fermentation, in addition to the changes in fermentation mass, temperature, and pH as fermentation evolved. As seen in the fresh whole bean and cut test pictures of a typical fermentation cycle, on day 0, a rich purple color due to the high concentration of polyphenols with rigin is observed before fermentation. On day 3, a decreasing purple color with increasing rigin is observed during fermentation. And on day 7, a brown color with noticeable rigin is observed, which is evidence of the breakdown of the viscellin proteins and polyphenols at the end of fermentation. Switching now to the fermentation dynamics, and specifically time taken for the fermentation mass to reach 45 degrees Celsius. There was a generally shorter time taken to 45 degrees as the season progressed, with a more pronounced decrease at Grand Couva. We observed a shorter time taken to 45 degrees Celsius with smaller fermentation masses. Grand Couva decreased by 24.9 hours from early to late season, whereas Santa Cruz only decreased by 1.5 hours from early to late season, with a more consistent volume of wet beans per fermentation mass. Time taken to the intersection of tester and cotyledon pH is considered an important parameter in the fermentation process, where the acidification process is completed and the microbial activity of acetic acid bacteria has been reduced. We observed a generally shorter time taken for the intersection of tester and cotyledon pH at Grand Couva, with a 4-hour decrease as the season progressed from early to late season. However, the trend was more variable at Santa Cruz, with a mid-season increase and then a decrease, with an overall small reduction in time taken to the intersection of tester and cotyledon pH. Finally, looking at time to maximum temperature and maximum temperature of the fermentation mass, we observed a generally shorter time taken to reach maximum temperature as the season progressed at Grand Couva, with a 22-hour decrease from early to late season. However, this trend was more variable at Santa Cruz, with a mid-season decrease and then a late-season increase. Overall, there was a marginal increase in maximum temperature of the fermentation masses. This is linked to a faster fermentation, evidenced by a shorter time taken for the intersection of tester and cotyledon pH, as well as to decreasing bean volume being fermented, especially at Grand Couva. I will now hand you back to Dr. Sukha to continue with our focus now on sensory attributes.
Thanks, Krystal. I'd like to focus now on a general comparison of the flavor profiles of the Grand Couva and Santa Cruz locations across the early, middle, and late season. As mentioned previously, I'll focus on the core attributes of cocoa flavor, total acidity, bitterness, and astringency, then on the complementary attributes of total fresh and brown fruit, total floral notes, followed by total woody, spicy, nutty, and sweet notes. And finally, I'll mention any off flavors that were observed linked mainly to some elevated fermentation. So looking at the early season, we see that the core attributes were at similar levels in both locations. There were higher fresh fruit and floral levels at Santa Cruz, and some low level of flavors present at Grand Couva. In the mid-season, we saw the core and complementary attributes were similar at both locations. Some nutty notes emerged in Grand Couva, and the low level of flavors disappeared in Grand Couva, but emerged in Santa Cruz a bit. With the late season, we saw the core and complementary attributes were at similar levels in both locations. The fresh fruit and floral levels increased in both locations, and some sweet notes also emerged in both locations. And most importantly, the low level of flavors disappeared at both locations. So now I'll hand you over to Vickeisha Lall, who will continue the conversation about the sensory attributes with some more focus now.
Everyone, I'm Vickeisha, and I'll just be walking you all through briefly some findings from the sensory assessment of samples collected from the Santa Cruz location. So for some of the fermentations we would have monitored, we would have pulled samples from the fermentation mass on days 4, 5, and 6 of the fermentation and dried these samples in small containers on the drying floor. So this was done to arrest fermentation at these earlier time points and compare the resulting flavor profiles to beans from the farm's entire fermentation mass, which I will from here on out be referring to dry and floor samples. So I'll just get started on my points now. So here I just want to focus on the intensity of fresh fruit flavor in particular. So on the horizontal axis of this graph, we have the fermentation endpoint. And so the day 4, day 5, day 6, and the drying floor samples. And on the vertical axis, we see fresh fruit intensity, which was determined by our panel after sensory assessment. So the individual dots in this graph represent individual fermentations. So as you can see, the red dots represent day 4, the green dots is day 5, blue dots is day 6, and the purple is the dry and floor samples. So as you can see, it appears that the day 4 fresh fruit intensities, so these are the red dots, are closer together. So they have like a smaller range compared to the other endpoints. So this indicates that the fresh fruit character of the day 4 samples was slightly more consistent compared to the other endpoints. So the average fresh fruit intensity for the drying floor samples was the lowest compared to the other endpoints. And that's mainly due to this purple dot here that the red arrow is pointing to. So you can see here that it had almost no perceivable fresh fruit character and the intensity is very near to 0. So this was actually the 9th fermentation batch that we monitored, which had the smallest fermentation mass of the entire crop year at 189 kilograms, sorry. So what we noticed was that fermentations progressed quicker for smaller fermentation masses. So as batch 9 was so small, as the mass was so small, this led to over fermentation, which produced off flavors, which tend to mask like the more desirable fruity and floral fine flavor notes. So that explains the very low intensity fresh fruit of this this purple dry and floor point all the way down here next to 0. Sorry. So now I'll focus on total brown fruit. This plot here is similar with the same color coding as the one on the previous slide, except this one deals with intensity of brown fruit on the vertical axis. So we see here that there are pretty small ranges for brown fruit. The dots are pretty much close together, indicating that brown fruit character is pretty consistent generally for each endpoint. The smallest range was again noted for day 4. And the last fine flavor attribute that I'll look at is floral. So if you look at the graph, which is again similar to the ones before, except on the vertical axis, we're looking at floral. No clear trend was really noted for floral. We saw the highest floral score occurring on a day 5 sample. And so now I'll look at off flavors or flavor defects. So these are unpleasant, undesirable flavors, which usually reflect some defects in the beans. The bar graph on your left just compares the average total off flavor for the different fermentation endpoints. You can see that there's a slightly higher average total off flavor for the drying floor sample. So that's the bar to the extreme right, followed by the day 6 samples. The graph on your right is again similar to the 3 I would have shown before, except it looks at total off flavor on the vertical axis. So once again, we have red dots for day 4, green dots for day 5, blue for day 6, and purple for drying floor. The numbers, however, labeling the dots represent the fermentation batches throughout the crop year. So if you look in particular at the points I have circled here in blue, you'll notice that they are the 9th fermentation batch. And I would have mentioned about this earlier when talking about fresh fruits, but this fermentation batch had the smallest mass of the crop year, and the fermentation progressed much quicker than the other larger masses, leading to some over-fermentation, and their associated off flavors. So from day 5, so that's this green circle dot here, we notice off flavors. And what we see is that the longer that this is left to ferment, the higher the intensity of the off flavors became. So the circled green day 5 dot here, you see it's just above 1. The blue day 6 dot next to it is higher, around 2.5. And then for the drying floor samples, as the purple dot, it's all the way up here at over 4. So we see this steady increase in off flavor intensity with longer fermentation in this batch as it became more over fermented. So now I will focus only on the drying floor samples. These would have been beans that were completely fermented and dried at the farm and without us altering the process in any way at all. So I'll represent the spread of the different flavors throughout the crop year using box plots. So box plots give information on how the data is spread out. So you can quickly compare like median, interquartile range, maximum, minimum values. However, if you're not super familiar with these concepts, don't worry. For this presentation, I just want you to simply look at the height of each box and the length of the lines above and below the box. And this should give you a pretty good idea of the range of the flavor intensities. So the longer boxes represent flavors that showed more variability or differences throughout the crop year, and shorter boxes represent flavors that are pretty much more consistent throughout the crop year. So just bear this in mind as I present the next 2 slides. So firstly, I'll look at the core attributes. So this is cocoa acidity, bitterness, and astringency. You can see the brown box here right away, which shows cocoa flavor. It's pretty short compared to the other boxes, indicating that cocoa flavor was more or less pretty consistent in this location throughout the crop year. However, if you compare this to the purple box on the extreme right, which represents astringency, you notice that this box is a bit longer, so it appears that the astringency levels varied a bit more throughout the crop year. And now, if you look at the table on your right, you'll notice that astringency is actually the only core attribute that didn't quite fall into the desired intensity range for the entire crop year for this location. Next, I'll just have a quick look at the complementary or the more fine flavor attributes. So straight away from these box plots here, we can see that the peach colored and the pink boxes are the longest compared to the other boxes. So the peach box is fresh fruit and the pink box is floral. These 2 flavors displayed the most variation throughout the crop year compared to the others. This might suggest that they are more affected by perhaps post-harvest process practices or possibly environmental conditions than the other flavors. The box for brown fruit is pretty short, which shows that brown fruit intensity was more consistent throughout the crop year compared to fresh fruit. And here circled in red, we notice that there's one outlier for fresh fruit, and this is once again the infamous small 9th fermentation batch. The table on the right shows the ranges and averages of each flavor next to their desired ranges. And we see that brown fruit was the one attribute that consistently fell in the desired intensity of above 3 for the entire crop year. Right. Okay, so I think that's it for me and my brief run through the trends from the century data. I hope it was at least a little bit insightful. I'll now pass you back to Dr. Sukha, who'll do the conclusions and the wrap up.
Thanks, Vickeisha. I'll now try to link all that we've discussed thus far into the notion of an evidence-based toolkit for monitoring cocoa fermentations to optimize bean and flavor quality. In looking at the fermentation dynamics, we can present the interplay of temperature and acidity measured as pH on this graph here against time on the x-axis. We can use temperature, the change in acidity of the tester and cotyledon, the external appearance of the bean, and smell as cues to track the progress of fermentation. And these can also be linked back to the wet bean quality, such as the degree Brix, the size of the fermentation mass, etc. But this graph shows the rise in temperature, which is the red line, as fermentation progresses, and the change in pH or acidity of the tester and cotyledon of the bean in the blue and green lines via the breakdown of the pulp and the acidification of the cotyledon with acetic acid. The point where the tester and pulp acidity are the same with a matching drop in temperature of the fermentation mass are actually critical cues to determine the optimal fermentation endpoint. Usually, the time taken to cross 45 degrees centigrade and the maximum fermentation mass temperature are important to note as well. Turning and mixing of the fermentation mass also boosts the fermentation rate. The optimal range of the end of fermentation from all that we have seen seems to vary between 4 to 6 days. What is important to note is that fermentation tends to continue for about 2 days after the beans are placed on the drying floor. This is especially important in rainy weather at the start of the drying process, where there is enough free water inside and outside of the beans to continue fermentation, where we have aerophilic bacteria and mold predominating, causing putrid or flavors. Some key take-home points now from the results are that nighttime temperature and daily relative humidity seems to vary more between the locations that we looked at. The degree Brix and the initial pulp pH seems to change across the season and the two locations. We seem to have a faster fermentation rate with smaller fermentation masses. There's a shorter time taken to reach the maximum temperature as a result. The optimal fermentation endpoint range seems to be between 4 to 6 days across the cocoa season. So there's no one day, but a range rather. And this is linked to nuanced differences in complementary flavors across the locations, mainly in fresh and brown fruit notes, as well as floral, nutty, and sweet attributes. We also have lower complementary flavors and higher off flavors if we have smaller fermentation masses and if they are fermented above 6 days. And initial drying rates affect quality even after optimal fermentation, as it extends the fermentation time and introduces off flavors. Temperature and pH with aroma and sensory evaluation seem to be good indicators to monitor fermentations, to give a holistic understanding of what to measure and to better manage spontaneous cocoa fermentations. So we now have a suite of tools for management of cocoa quality and to generate useful information for certification locally, regionally, and internationally. Finally, I would like to acknowledge the farmers and the workers at the two locations who are active partners in the data collection process. Thank you very much. And we are now building on this work with an even deeper dive into fermentation metagenomics. So I would now like to end here and to take some questions.